take the keywords, or I try to summarize the explanation in the textbook. So basically, okay, so to analyze external convection problems, okay, first you need to define the flow geometry, the system geometry and the flow geometry. Meanings, the flow geometry means you need to know whether the flow is in the parallel or in the normal to the surface or the system. Okay. So first one, you need to determine the flow geometry. Okay, meanings that you need to know whether it is a plate or it is a cylinder or whether it is a sphere. Okay, and you also need to know whether the flow is a parallel or is a normal to the surface that you are interested to study. Okay, because these two conditions will be affect the area, the effective area that you will be analyzed, as well as the correlation that you will choose. Okay. Next one, you need to specify the reference temperature. Why? Because this reference temperature will be used to calculate the fluid properties. Okay, so the fluid properties can be a liquid or can be a gas. Okay, so in order to find the right fluid properties, so you need to find the film temperature. Okay, in this case, the reference temperature known as a film temperature. Sometime in other textbook, they call film temperature is an average temperature. Okay, it's average temperature between the surface and the fluid. Okay. The okay, blue. Okay, the third one. Okay, so what the properties that you need to define? I think depending on the further calculation, but normally what the properties that you are interested is density, what the thermal conductivity, the viscosity, Prandtl number. Okay, sometimes you need a specific heat. Okay, so this is the typical properties that you require, okay, in order to use in the further calculation. Okay, so next one, once you identify the properties, okay, so you need to calculate the Reynolds number. And okay, Prandtl number is actually you can get the Prandtl number directly from the table. So this is one, but you need to calculate the Reynolds number. Okay, so you need to calculate the Reynolds number. Okay, then after you calculate the Reynolds number and you know the Prandtl number, you need to know whether your problem is looking solution for the local. So you know what is the local, or whether it is average. Okay, so local means specific point. Okay, like we discussed yesterday. Average means it is an entire system, the whole system. Okay, probably you want to look the how much the heat transfer from the whole system, not at specific point. Okay, specific point meaning probably you want to find heat transfer at the middle, heat transfer at the end of the plate, or probably at the early part or at the edge of the plate. So that is the problem that normally represent, you need to find the local coefficient. Okay. Next one, once you know Reynolds number, you know your local or average, and you know from the Reynolds number, you know whether it is a laminar or turbulent, then you need to choose the Nusselt number correlation. Okay. So normally in external convection, they already put in the table 7.9. In fact, I'm not sure whether this table is the same table in your recent textbook. It is table 7.9. Table 7.9. Why I don't have this table? Probably can. I think this is the old one. So neglect this my my writing here, table 7.9. You just need to find the Nusselt number correlation. Okay. How it looks like. Okay, this is for example Nusselt number correlation. Okay. So Nusselt number equals to some number, Reynolds number, Prandtl number. Okay. I can put it in the general relation. Nusselt number equals to C Reynolds number to the power of m, Prandtl number to the power of n. So try to look into this kind of form. Okay, Nusselt number, this equation. Okay. So then if you think that is the right or suitable Nusselt number, so you need to calculate Nusselt number for the characteristic length scale. Okay, meaning you need to calculate this Nusselt number first, and then this value will be equivalent to the Nusselt number equal to HL C divided by K. Okay, this is the general equation for the Nusselt number that have relation to the heat transfer convection coefficient. Okay, this characteristic length scale is this one, LC. Okay, so this is a LC. So from this you can change into the rearrange into the H form. So H equals to Nusselt number times K divided by LC. Okay, then you can get the H value. Okay. So once you get the H value, so you can apply to the original heat transfer convection, which is H delta T. Okay, if you move here, AH delta T. Okay, so all these steps from 1 to 6 is just to find what is. So seems that the process to find the H is actually not straightforward. Okay, is a bit not say complex, but is a function of the properties of the fluid flow, okay, as well as the flow geometry and the system. Okay, any question? Okay, so if you can understand this process or this step, okay, in terms of calculating external convection analysis, so we can go to the go back to the some cases of heat transfer system. For example, this is flow over flat plate. Okay, I skip this first. Okay, So you can see there is some coefficient. Okay, I'm not cover this because it is the same thing. Okay, if you are looking for the drag force, then you need to calculate this value as well. Okay, because the process is the same. You need to find you need to know the flow type, you need to find the properties, you need to calculate the Reynolds number, then you can calculate this friction coefficient. Okay, because from the Reynolds number, okay, first you need to calculate the film temperature. Okay, and then you need to find the properties. You need to define the calculate the Reynolds number. Then you know whether it is a laminar or turbulent. Okay, then you can choose which one. Okay, and depending whether you are looking local or average, entire, whole. So if you are looking for the whole, then choose the equation without subscript x. If you are looking for the local value, then you choose the equation that have an x term. Same goes for the turbulent. Okay, so what is this for? This one is used to calculate drag force. You remember drag force can be calculated if you know the drag coefficient rho a v squared times the drag coefficient, and the drag coefficient is coefficient due to the friction plus coefficient due to the pressure. Okay, remember for this case, no pressure because it is a parallel flow. Coefficient due to pressure is um, very small and can be neglected, and that's why this value is a 0. So you can get direct from either this equation for turbulent or laminar or for the local. Okay. Okay, this is just to how this equation. I should explain how this equation can be obtained. Okay, but for me, it requires some time because basically is just integrating the element of the boundary layer to the as a function of x direction. You can look to the some example here how they got the final equation here. So I just explained how to use the equation rather than how to derive the equation. But if you want to see how this equation is obtained, then you can go to the explanation in textbook. How its coefficient can be derived from the original equation of the element, okay, as a function of x. Okay. Okay, this is for the case of laminar and turbulent, meanings that you are considering transition condition. Okay, not always, because normally it is only happen within the specific Reynolds number. So if you calculate your Reynolds number within this range, so you should use this equation. Okay, you have to remember, even though you calculate, let's say you calculate Reynolds number equals to 1 times 10 to the power of 6, which is, you say this is a turbulent, then we should use the turbulent one. Okay, but why there is a laminar terms in this equation? Okay, so you need to go back to the, you need to understand the geometry of the flow on top of the surface. Okay, so you get the Reynolds number 1 times 10 to the power of 6 is at this point. Okay, so in here, the Reynolds number equals to 1 times 10 to the power of 6. Okay, meaning probably at this region, so where is the critical value? So the critical value probably 5 times, sorry, not 5, yeah, 5 times 10 to the 5 probably is somewhere in the, not say middle, just a quarter from this length. So what happened at this region? So this region is basically a lamina. This is a turbulent. So that's why when you calculate the overall friction, then you need to consider the laminar terms and the turbulent terms. So that's why we have these two terms. Okay, so one is considering the laminar, another one is considering the turbulent. Okay, this is only for the friction coefficient. It's slightly different for the heat transfer. Okay. Okay, I try skip. Okay, so for heat transfer, like I say, you need to choose the right Nusselt number based on the Reynolds number value and the Prandtl number value. Okay, so if you recall back the step of calculation, so you need to find the flow geometry. Okay, so that you know the area, and then you need to calculate the film temperature, the average temperature. So you define your properties. So you calculate Reynolds number and you know your Prandtl number. Okay, so you choose, because actually from the Reynolds number you know that whether it is a laminar or turbulent. So you can choose whether it is a laminar, okay, or it is a turbulent. Okay, and whether your problem is a looking for the local solution, or you want to solve the whole system, whole solution, entire solution or average solution. So if you are looking for the local, then find the X one. Okay, because you should know what is the X value. But if you're looking for the whole solution, then you choose without X. Okay, the one that I put in the red border. Okay, so how to choose this equation? This equation only valid if the Prandtl number is larger than 0.6 and your Reynolds number less than 5 times 10 to the power of 5. Okay, actually this one is the same condition. Same goes to here for the turbulent. Okay, it should be within 0.6 to 60 Prandtl number, and the value is between 5 times 10 to the power of 5 until 1 times to the power of 7. So the Nusselt number might be in table 7 too. Okay, so this means I need to change my note. 7.2. Let me check 7.2. Yes, 7.2, but it's not complete. Okay, it's not complete. Okay, so never mind. Table 7.2 is just a part of the equation. There is many actually. Okay, we will go to the textbook after this. Okay. Okay, any question about this equation? Nusselt number and friction coefficient. So while, okay, why this laminar turbulence flow is very important? Okay, look to this graph. Okay, this graph is already is actually available in your textbook. Okay, so if you look to this graph, okay, where is it? Figure 7.9. Okay, so this is a variation profile of the convective coefficient, heat transfer coefficient for the H at X at specific location, and also the variation of friction coefficient when it is laminar, transition, and turbulent. Okay, so what you can see at the, let's say this is your plate, your interested plate. So once the flow is facing the first edge, the first part of your system, or of the plate, it start to slightly higher. Okay, start with the higher value and then reduce gradually. I can say reduce gradually. Okay, until it become minimum, at which the lamina start to transform to the transition. Okay, what do you think? This what is the value of this? So basically, this value is at Reynolds number 1 times 10 to the power of 5. Okay. So once it is moved to the further transition, probably this is close to the turbulent. Reynolds number equals to 5 times 10 to the power of 5. The heat transfer convection coefficient will be what? Increase significantly. Okay, in the linear portion, in linear relation. Okay, which is very high compared to the highest value in the lamina. So the value will be higher than the lamina situation. Okay, so this means when you compare the H value, so H value for the turbulent should be higher H value for the lamina. Okay, this is what this figure is explain the trend, the scenario. Okay. Same goes to the friction coefficient. Cf x for the turbulent will be higher than Cf x for the lamina. Of course, right? Because due to the fluctuation, or this one, fluctuation of the flow movement. Okay, there is a fluctuation, but very uniform and smooth. Okay, in terms of randomization. Okay, so this flow characteristic, laminar, transition, turbulent, clearly affect your drag force. This one is to calculate the drag force, and this one to calculate Q, H, A, delta T. So once H increase, Q also increase. Okay, so that's why it is important to define whether it is a laminar, transition, or turbulent. Okay. So in case of laminar, okay, if you look to the previously, you got a laminar and you got turbulent, and you got another equation for the laminar and turbulent. Okay, so what do you think? What the difference between this equation and the case of the turbulent? Okay, can you imagine? You have, okay, you have a laminar case, you have a turbulent case, and the third one you have a mix between laminar plus turbulent. Okay. How you, what the difference between the turbulent and the mixed laminar and turbulent? Okay, under heat transfer we have a three possible equation that you may use to calculate the H value. Anyone want to explain? No? So for the case of lamina, okay, let's say this is your plate, okay, you may say that when you calculate the Reynolds number from 0 to this L value, so the whole how to draw, the whole flow is in the lamina profile, okay, until the end of the plate is still in lamina. Okay. Number 2. Okay, turbulent. Number turbulent. I need to have some space here. So how you may consider turbulent? Okay, I think I explained the lamina and turbulent first. For the case number 3, you got a plate with certain length L. Okay, so at the some part you got lamina, at the some part you got a turbulent. Lamina, this is transition, and this is turbulent. Okay. Okay. So this is your plate. So this is a flow. So you got lamina and turbulent. So this is for number 3. But how about the turbulent one? You may find at some cases you have a lamina here, very small, but the whole, the major part, this is lamina, this is the turbulent. The turbulent is dominating the major flow on top of the surface. Okay, probably 70%. 70% of flow is dominated by the turbulent flow. So in this case, it will be turbulent equation. Okay, this is more applicable when you dealing with high velocity. Okay, and probably high friction coefficient. Okay, but if you have some very moderate velocity, then you may have this kind of pattern. And it is long enough, you may get lamina and turbulent. But if it is very short, probably you got a lamina. Okay, so it's depending on the situation. Okay, depending on the L value, depending on the surface roughness, and depending on the properties of the fluid. Okay, the velocity and the density, viscosity, and so on. Okay, so meaning that even though there is a lamina and turbulence, so there is possibility of you got the full condition of the flow is a turbulent. Okay, because of the turbulent dominate the major area, the major space. Okay, of the convection phenomenon. Okay, I think this one, the previous equation is for the normal liquid, okay, normal gas and normal fluid. Okay, there is also equation if you are using liquid metals. Okay, what is a liquid metals? Liquid metal is when the Prandtl number is small. Okay, what is the example of the liquid metals? The common one that you use is Hg. What is Hg? Mercury. Okay, mercury is the liquid metals. So if you're dealing with liquid metals, then you need to find the H value because you want to calculate how much the heat transfer through the mercury. Then you need to use this equation. Okay. Okay. So there is another equation here, all fluid. Okay. What is the difference this equation with the early equation? Okay. What the difference between this equation or this correlation, okay, with the previous equation of laminar and turbulent? Okay, so if you using this equation, okay, you can read from the textbook. Normally, this equation can be applicable to any kind of fluid and any kind of flow type. Okay, whether it is laminar, transition, or turbulent. Because you can see the equation will be a bit complex. Okay, because you are having another terms of Prandtl number with a different factorial. Okay, in as a dedominant. Okay, so if you may ask which one I want to use. Okay, so it's up to you. If you want to use a simple equation, okay, you can use either the first, second, or third. But if you want to use more lengthy equation or lengthy correlation, okay, you can use this one. Okay, but to use this one, this condition must be meet. Okay, which is Reynolds number times Prandtl number is greater than 100. Okay, sometimes when you choose it is not meet the condition, then you have to go back to the original or the earlier equation. So that's why before you want to choose, make sure the equation that you choose have the condition that meet the problem that you are currently doing. Okay. Okay. So let me see some of the equation in the textbook. Okay. So if you look, okay. Okay, this one. So if you look, probably it's very small. Okay. Okay. If you look, this is the heat transfer coefficient for the laminar and turbulent, but local, because of you got this x value. So you got this x value, and you should meet the condition here in order to use that particular equation. Let's say you not meet it. Okay, let's say you got the Reynolds number, what? Reynolds number 1 equals to 10 to the power of 8. So then how to use this? So it's not meet. Then you can use the other equation. Which one? Where is it? This one. Okay. You may use this equation if the condition of the previous one is not met. Okay. Okay. So you can use this equation. Okay. Hopefully, the condition here at the higher Reynolds number, 1 times 10 to the power of 8, of course, right, because this is 100. So the times between the Reynolds number times the Prandtl number should be greater than 100. So I believe this equation used for the larger Reynolds number. Okay, even though I also rarely to use this kind of equation, because it's really hard. It's really difficult to find the Reynolds number greater than 1 times 10 to the power of 7. Okay, normally in any kind of problems. Okay. Okay. Before that, I want to check table 7 too. Where is table 7 too? table 7.2. I'm not sure whether it is the same. This is 7.1. This is 7.2. Yeah, 7.2. 7.2 is for the cross flow over the tube banks. Okay, Nusselt number. Okay, I think this is not covered in our syllabus. Okay, because we will not have, not say because of it's not important, but because we don't have enough time to cover whole kind of geometry. Okay, this one is for the cross flow over the tube banks. Okay, where is it? Tube banks, normally in the boiler, heat exchanger. Okay, where you find there is a lot of tube banks. Okay, by apply to the specific system, then you need to choose this kind of equation. Okay. Okay, back to the slide. Okay, case 2. Okay, you may find at some cases the plate that you are analyze have some heat flux. Okay, experiencing some heat flux. What is heat flux? The plate is exposed to the certain heat flux. Okay, probably the heat flux can be come from the electrical heater, or can probably come from the other source like sunlight. Okay, heating element from other equipment. Okay, so this is kind of scenario or situation you need to consider flow over plate but with uniform heat flux. Okay, because why? Okay, why under this case you need to have specific equation. Okay, okay, what is the difference between the earlier one? Okay, so if you looks to the earlier one, okay, the earlier one is for the uniform surface temperature. Okay, case one, let me go back. Okay, this one. Okay, flow over isothermal plate. Okay, I'm not sure whether you are aware or not. Okay, so the original equation here, this Nusselt number is under isothermal plate. What is meaning by isothermal plate? Ts is a constant. So the surface temperature of the surface temperature is constant at specific value, fixed specific value. Okay, but in practically it's hard to constant the surface temperature, but it is more easy to expose the surface with the constant heat flux. Okay, constant heat flux can be come from the electrical element or the sunlight. Okay, the heat source. So under uniform heat flux, you should use other different Nusselt number equation. Okay, for laminar and for the turbulent. Okay. Okay, any question? Okay. Do you have any question? Really? From this slide, you don't have any question? If you don't have any question, I have a question for you. Okay. So if you look carefully, for the uniform heat flux, you only have a local equation. Yes. Okay. So how to use equation for the average for the entire plate if it is a heat flux? So in this case, you can use in the Nusselt number for the Ts constant. Okay, so this is a kind of assumption. Okay, so we assume that the average condition for the heat flux will be same as the average condition under uniform surface temperature. So under uniform heat flux, if you want to calculate the H for the entire plate, entire system, you can use the Nusselt number for the lamina for the case of specific constant, and same goes for the turbulent. Okay, don't say in the question that the equation is not available in the textbook. Okay, actually, if you read carefully the description in the textbook, it is say that for the entire plate you can use the previous equation, okay, of the surface temperature constant. Okay, understand? Okay, okay, let's we do some look some example. Okay, hopefully you can get more understand from the example. This is example from the textbook. Okay, quite easy. Okay, in fact, straightforward because they show you how to do this. Okay, so this is an engine oil. Okay, actually this problem is try to simulating or try to represent what happened inside the engine compartment inside the engine. Okay, so you have some surface, probably this is the piston surface, and you have some oil pass through this surface with a certain velocity of 2 meter per second. Okay, and with the temperature of 60 degrees Celsius. Okay, the velocity is 2 meter per second, and the surface temperature of this surface is 20 degrees Celsius. Okay, so the surface temperature is 20 degrees Celsius. So in this case, you can say that this case is a Ts constant. Okay, because the Ts value is given. Okay, determine the total drag force and the rate of heat transfer per unit width, Q divided by W, okay, of the entire plate. So what is meaning by entire plate? So this is, you need to find the average value. Okay, you need to find the average value of the CF and also the H, okay, without the X subscript. Okay, so if you look to this solution in the textbook, this is example. First, define the properties. How to define properties is between the film temperature and the the surrounding temperature, fluid temperature, and the surface temperature. Okay, so 20 plus 60, so you got 80 divided by 2, 40 degrees Celsius. So for 40 degrees Celsius, find the engine oil properties at 40 degrees Celsius, so you got this value. Okay, so after you got the value, So from the length of 5 meter, so you calculate the Reynolds number. So velocity time the length time the kinematic viscosity. So they're using kinematic viscosity. Okay, so they don't use the density. So you got this value. So laminar or turbulent? If you not see the this one, laminar or turbulent, guys? Four times 10 to the power of 4. Okay, so your reference is critical value is a 5 times 10 to the power of 5, or you want to make it more strict, 1 times 10 to the power of 5. So anything below this is a laminar. So this is a laminar. So when it's laminar, so you need to find the you need to calculate the drag force, right? So you need to find the friction coefficient for the laminar. So where they got this value 1.33. So where is it, the laminar? Oh, it's a bit difficult because I have to scroll. Okay, this one. So you need to find convection friction coefficient. Okay, friction coefficient, laminar, entire plate. Okay, so friction coefficient here. So this is local. So this one laminar. So you need to take this value. CF equals to 1.33 divided by Reynolds number to the power of half. Okay, so this one 0.5 half. So you got this value and you put it into the calculation of drag force. Half times rho AV squared times CF. The same thing. Okay, so you got this value. So next one, you need to calculate the H. Okay, so how? You need to find, you know that it's a laminar. So find the equation of Nusselt number for the average or entire system under laminar condition. Okay, so this is the value. So you know the Prandtl number, you know the Reynolds number, you calculate, and this is equals to 1913. Okay, so 1913, rephrase or reuse the equation using the Nusselt number equation HL over K. So try to find H value with a given K from the properties, L value from the length. So you got this one. Okay, so from there use HA delta T. Okay, so you got this value. Okay, quite straightforward, right? Okay, sometimes you need to check whether your H value is logic or not. Okay, remember you have a chapter 1 where there is a table of the H value, the typical H value for the free convection, H value for the forced convection. Okay, and in fact you got for the gas, you got for the liquid, you got for the gas, you got for the liquid. So you can use this table to check whether your value is logic or not. If you got not logic, probably you need to recheck your your calculation. Sometimes you forgot to use this power factor. Okay, you write 0.5, but when you press the calculator, you forgot to put the 0.5. Okay, this is a common careless mistake. Okay, any question? Okay, this is You want to take 5 first before we do some other example from the problems, or you already take 5? Okay, I think I want you to okay, I choose one example, one exercise. I think this exercise is much better than the this exercise is similar to the problem in the text, in exercise in the textbook. Okay, because it's calculating the drag force. You know how to calculate drag force. You can check heat transfer. Okay, this one example 718. Okay, it is same like in your textbook. This is example from the textbook. That's exercise from the textbook, not example. Exercise from textbook. So this is entire plate. This is entire plate. This is a local middle section. Okay, so this is a local. Okay, this is a whole average. Same here. Okay, I think I want you to do this problem. Okay, this one is more interesting. Okay? In fact, your project, okay, can be used. Originally, I want you to calculate the H value from the project, but seems too much compared to the, I mean, with the current requirement of calculating conduction. I think I will put aside. But if you have a time, you can put in your report as well. Okay, how to calculate the H value as part of the analysis, if you want. Okay. Okay. Take 5 first while you read this one. Okay, while others try to understand this equation. Okay. We take 5 first. Those who want to already take 5, you can read this problem, how to solve this problem. Okay, this is a heat flux problem. Okay, heat flux condition. You can look from the textbook this problem. This is for the air focus. Table in 30. Saturated water. Saturated air. Atmospheric air. Okay. Okay. Those who are already in the front of your PC, you may try to do this example exercise so that you can get a good understanding. Okay. 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 I need to find some blank page. Okay. Where is it? This is class attendant. Okay. This one. Can you clear? Can you see the problems clearly? It's a bit small. Okay. So this problem of external convection analysis. Okay. So like previous, same like a previous any problem of heat transfer, or in fact any engineering analysis. First, you should start with your schematic. Okay. So you can draw a very simple. Let's say this is the let's say this is the what the front of the train. Okay. So the train is moving. Okay. The train is moving in this way. So basically it will be facing some resistance due to the air. Okay. At what 70 kilometer per hour. Right? 70 kilometer per hour. So this is the train moving. Okay. So we can put some tire to show that it is actually a vehicle moving in the certain direction and velocity. So the air surrounding in here is at 30 degrees Celsius. Okay. The top surface of the passenger car of a train moving at a velocity of 70 kilometer per hour. Okay. Okay. So our interested section is only the top surface. Okay. So this is our interested area. Okay. How can I draw this? Okay? The one that I shaded with this light brown, okay, is our interested area. Okay, so with 2.8 meter wide, so the length, the wide, the wide is a 2.8 meter, and the length is a 8 meter. Okay, I think this is only the front car of the train. Okay, it's not all. If all, then you have to increase the area. So the top surface is absorbing solar radiation at a rate of 200 watt per meter squared. So that means the top surface is exposing to the heat flux. Okay, Q dot equals to 200 watt per meter squared. Okay, so the heat flux from the sun. Of course, it is due to the only heat come from the top is due to the sunlight. Okay, radiation from the sun, and this is 200 watt per meter squared. The temperature ambient is 30 degrees. Okay, so assuming the roof of the car to be perfectly insulated and the radiation heat exchange with the surrounding to be small relative to the convection. Okay, radiation heat exchange here, meaning that whenever radiation coming, so there will be some radiation exchange, reflection. Okay, but this reflection we assume it is small and can be neglected. Okay, so I can say that the heat transfer that occur in the top space is come from the radiation. Okay, and this can be calculated into the convection coefficient. Okay, meanings Q, sorry, sorry, I need to delete this. So meaning that Q convection on the top area equals to Q by the radiation. Okay, and since this is giving you the area, so basically Q convection at the top is equals to the Q radiation by the sunlight, and this equals to 200 watt per meter squared. This is what this word is meaning. Assuming the roof of the car to be perfectly insulated and the radiation exchange with surrounding to be small relative to convection. Okay, so the convection that occur in the top surface is mainly due to the radiation of sunlight. Okay, because if you look to this equation, so the H value, okay, so the question asks you to calculate what determine the equilibrium temperature of the top surface of the car. Okay, so you need to find the TS value. Okay, find TS. Okay, so find the TS. How to find the TS? You know this value, Q convection top. Okay, H Q convection at the top equals to H TS minus T surrounding, right? Okay, TS minus T surrounding, and this equals to 200 watt per meter squared. You need to find this. You know this, but you also don't know this. So you need to find H first. Okay, you need to find the H first. So how to find the H? Using the method that we described just now. Okay, using the correlation. Which correlation? Depending on what condition that the the flow will be. Okay, I delete this because I want to have the we will go back to this equation later. Okay, to erase very fast. I don't know. Okay. Okay, how to, okay, next one, number 2. After we draw the schematic, then we should state our assumption. Okay, so what is the assumption? You can take from the problem as well. Okay, assumption say that the radiation heat exchange to the surrounding is small and neglected. Okay, what else? Steady, because this is not transient, steady state condition. Yes, steady state condition. Critical. What do you mean by critical? Aiman. Critical properties. Oh, okay. Yeah. You can put yes. Right. The reference of your criticals, the critical Reynolds number, okay, is occur at 5 times 10 to the power of 5, because like I say, some people use critical Reynolds number is at 1 times 10 to the power of 5. Okay, some using 2, okay, some using 5. So if you put this, so you know that whatever you got the value, then you have the reference to check. Okay, 4, what this air is an ideal gas with constant properties. Air is an ideal gas with constant properties. Okay, air is an ideal gas, is an ideal gas. Ideal gas with constant properties. Okay, normally we use constant properties, constant properties, because we want to say that the value of the properties will be not changed from time to time. Okay, even though the pressure and temperature will be slightly different. Okay, due to the unsteady situation. Okay, next one, number 3. So after you state your assumption, what next? Find the properties. Okay, find the properties. So your working fluid is a air. Okay, and because you already mentioned here air at atmospheric condition, right? Because why it is atmospheric? What are the term that I can say it is atmospheric? This one, ambient air. Okay, so ambient air meaning that the air is at one bar or 1 atmospheric pressure. Okay, so you need to find the T average, which is T what? T you only have 30 degrees Celsius in film. So T It's supposed to be T surrounding plus TS divided by 2. So you need to find the TS, but you need to use in the estimating the average of film temperature. So what is the TS value at this case? Okay. So what is your approach? Because we want to find the TS, at the same time we want to use TS in the estimating the average value. So what you can do here, you need to put another assumption here. Assume TS is equals to 30 degrees Celsius. Okay, same as the which is same as ambient temperature. Okay, or you also can say that probably 35. It's up to you. Okay, because if you why I choose 30? Okay, because I want to how can I say that? I want to simplify my calculation. If I put 30, 30 plus 30 divided by 2 is a 30, right? But if I choose 35, so you will got some different number. And you got some equation, you got some decimal point. Then when you go to the table, you have to do some interpolation. You got what I mean? Okay, you have to, but this is just assumption. Okay, your assumption, your accuracy of your assumption will be depending in your based on your final answer. Okay, you will check your assumption whether it is correct or not when you got your final answer. Okay, so in this case, I assume 30 degrees Celsius. I not assume 35, which is I also can assume 35. Okay, but I just choose 30 because I want to simplify so that the average temperature, the properties that I took will be at 30 degrees Celsius as well. Okay, otherwise you have to find at 35, let's say 35, 65, 32, 30, no, 30, 32.5, which is you need to do some interpolation. Okay, so air properties at 30 degrees Celsius. So where is the table? My table ini. Okay, this is the table. Okay, you go to the table A15. Okay, nampak tak? It's a bit small. Hopefully you can see clearly. If you have your own textbook, should be fine. Okay, so find the value of 30 degrees Celsius. Okay, Haikal already assist me. Okay, the K value equals to 0.025. Okay, if you want to check table A13, okay, 0.02588 watt per meter Kelvin. What else we want? We want the density. I want the kinematic dynamic viscosity. I want the Prandtl number. Can someone write for me this value? V is a kinematic viscosity, right? Okay. Oh, sorry. Haikal, that is okay, kinematic viscosity. So 1.608 times 10 to the power of negative 5. Okay, meters squared per second. Okay, density no need. Prandtl number 0.7282. Okay. The next one, once you get the properties, you can calculate the Reynolds number. So Reynolds number equals to what? V, because you got the velocity, V times L divided by kinematic viscosity. Okay. So what is the velocity? Velocity is 70 kilometer per hour. So you need to change. The V is a 70 kilometer per hour. So you need to change into meter per second. How? Divide by 1000 times 3600. Correct. 1 hour. Okay. 1 hour. Multiply by 1000. Divide by 6600. Berapa? Can you calculate the velocity in meter per second? 19.44. Okay, thank you. So 19.44 times the L. How much the L? L is 8 meter. Okay, 8 meter because the length of the surface, okay, parallel to the flow. Okay, divide by 1.608 times 10 to the power of negative 5. How much? Your Reynolds number? Nine point six 9.674 times 10 to the power of 6. Oh, so this is so laminar or turbulent? Turbulent. Okay. So basically flow is turbulent.